Okay, it's exactly 9 a.m. and we can start. And today we will continue introducing Maxwell's equations, right? We started doing it in the previous lecture, and now we just need to finish it. So pretty much, writing Maxwell's equations in this course, for me, it's like reaching the top of the course, right? Sort of the pivoted point, the top of the course, right? The top of the mountain. That's why I put this mountain, right? Okay, so and now let's quickly review what we've done in the previous class, because today we're going to continue, and then we will continue introducing new material. Okay. So you remember we decided to revisit Ampere's law. We've used it many times, so we feel like an experts, and so we decided to revisit it in order to introduce the rule, well-defined rule, which we must use in order to find the value of this enclosed current, right? So let me again remind you what was the rule. So every time, you remember, when we apply Ampere's law, first of all, we pick an Amperean loop. It can be any loop, right? So let's say we picked, but it must be closed, right? So let's say we pick this loop. This is our Amperean loop. Then we need to find which current is enclosed. So the rule is this. So after you pick an Amperean loop, you need to make the second step, and you need to pick a surface, any surface, enclosed by an Amperean loop or bounded by the Amperean loop, right? It can be, for example, flat surface, or it can be some kind of baggy type surface, complicated. It doesn't matter which. You should be able to pick any surface your soul desires. And then if a current physically crosses your chosen surface, then that current is an enclosed current. It's a well-defined rule, right? Because now basically you need to find if a surface and a line current is basically an infinitely long line, right? If they intersect. And if they intersect, then of course that is an enclosed current. And it doesn't matter which surface you pick to find enclosed current, everyone must end up with exactly the same enclosed current. So there's no discriminations on the base of your chosen surface. So any surface, should end up with, must end up with exactly the same enclosed current. Right, so, and then after introducing this, we looked at our typical example, and of course we found that it worked. Right, it worked, and that's why we use this Ampere's law for many times. But then Maxwell came, I told you, troublemaker, and he found an example where it failed to work. And next we looked at this example. So basically now we inserted a capacitor, right? And again, the same Amperean loop, right? We picked and following Maxwell's ideas, so we discussed two surfaces. First, the flat one, surface S1. In that case, enclosed current is I. So we looked at that, and that was a result of application of Ampere's law. And then Maxwell picked the second surface, because you can pick any surface you want. So he picked that second surface which goes through the gap in the capacitor. Why not? You should be able to pick any surface. So he picked this. And now there is no current crossing that surface. Current goes through this sort of hole in the surface, right, and stops at the positively charged plate. So this current I doesn't cross our surface S2. Okay, and now if you apply Ampere's law, you will end up with this equation. And zero enclosed current. How come? You remember the rule. It doesn't matter which surface you pick, everyone must end up with the same enclosed current. But now we pick different surfaces, and we ended up with different numbers. As a result, Left-hand sides are exactly the same, right? Left-hand side, because we integrated over the same Amperian loop. So left-hand sides are the same, but the right-hand sides are different, obviously. There's something fishy. Okay, there's something, okay, not, I wanted to say wrong, not wrong. Something is not complete. All right, something is obviously missing in the current form of Ampere's law. And it's obviously that something on the right-hand side of the equation, on this side, mu naught times current, because left-hand side doesn't give us any troubles. It's exactly the same, but the right-hand side. So it looks like some kind of current is missing on the right-hand side of the equation, right? So we need to add some probably additional term maybe in order to make this law work. So Maxwell found this problem, and good for him, he managed to fix this problem. He managed to solve this problem, right? And basically, he needed to find some additional term which has units of current and add it to the right-hand side of the equation, hoping that it will work. What I'm going to present now, basically his sort of logical steps, it's not a derivation, no way. It's more, I would call, fudging. And strictly speaking, right, most of the equations in physics, fundamental equations are written in this way. For example, like I remember equations in hydrodynamics, right? So physicists will see, okay, something is happening in liquid over there, right? Something, right? So in order to describe that, we need to add additional term, and they start fudging it, start putting terms to some factors together, some variables, right, in order to explain that phenomena. Once they manage to put together something which explains that, okay, they feel happy, right? And then once they found another phenomenon, they'll start creating something new in order to explain that. Most of the fundamental equations are written in this way in order to explain what they observe. Fundamental equations cannot be derived. All right, so that's what Maxwell did, right? So now I'm going to show you his steps. And again, it's not a derivation. It just, his goal was to come up with an additional term which has units of current, very important units of current, because we need to add it to the right-hand side of the equation, right? And then we'll see if it works, right? If it works, okay, you are the winner, right? So you will get your Nobel Prize, right? You will come up with some stories how, I don't know, how the light descended on you and you saw that additional term, right? And everyone would believe you and give you a standing applause, right? If you are the winner. Okay, so now let's see what Maxwell did in order to write that additional term. So, since it failed to work in the presence of a capacitor, so of course he started playing with parameters of a capacitor. So he needed to get, again, units of current, a term with units of current. So it means that if I write down, for example, charge of the capacitor using some values, right? And then if I differentiate the charge with respect to time, I will definitely get units of current, right? You see the logic. So first write down charge in terms of something, then differentiate it with respect to time, and obviously you will get units of current. Okay, so that's what he did. So let's write down expression for the charge inside of the capacitor, charge of the capacitor. Okay, so we can use just definition of capacitance. C equals Q over delta V. And here's the charge. So let's just solve it for the charge.
Once
you
ask the question, shoot herself with the answer.
Okay.
After,
Guys,
like, she has no patience. I don't know how she will feel.
Okay. Okay, so let's solve it for the charge. It will be C times delta V. Q equals C times delta V. And again, now, look, you remember we want to fix or adjust fundamental equations. Ampere's law is one of the fundamental equations, right? So it must be written in terms of fundamental quantities: electric field, magnetic field, current, charge, right? And these Capacitance, no, it's very useful quantity in the world of electronics, right? But it's not a fundamental quantity. Potential difference, again, potential difference, electric potential is not a fundamental quantities. You can look at any fundamental equations and you will never find these quantities. So let's rewrite them in terms of something fundamental. For example, delta V, instead of delta V, we should be able to introduce electric field. Okay, so C, expression for the electric or for the capacitance of a parallel plate capacitor. You remember C, epsilon naught A divided by D. And instead of delta V, potential difference between the plates, of course we can use E times D, right? So now let's plug them. And so that is C, epsilon naught A divided by D, and this is delta V, E times D. So of course D gets cancelled, and we're going to get universal constant, electric field inside of the capacitor times area of the plates. And now at this point, you should be able to recognize what is this? E times A, right? You see, E times A, what is that? It's a, okay, there is an electric field and there is a surface. What is that? And their product, it's the electric flux. It's electric flux, the value of the flux, number of the electric field lines crossing a surface of the capacitor. Okay, so let's replace this E times A and write as an electric flux, phi sub E. You remember, months ago we introduced that. So now we're getting charge equals universal constant times electric flux. Okay, it sounds promising. Now we're getting some construction in terms of fundamental quantities. So now what's the next step? We want to get units of current, so we need to differentiate this with respect to time. Like you see, dq over dt equals I. So obviously you will get units of current, okay? So I equals dq over dt. And of course, it is equal to the actual current which charges the capacitor, right, from the other side. Okay, and from this side, if you differentiate this with respect to time, you will get that. d over dt, epsilon naught times phi. Epsilon naught is a constant, universal constant. Let's take it outside of the sign of differentiation, and you're getting this new construction. New construction which has units of current. That's what Maxwell sort of derived, fudged, right, derived. And he gave it a cool name. So he decided to try this. He gave it a cool name, displacement current. Don't try to understand the meaning of this name, displacement current, because there is no meaning. Back then, 150 years ago, or maybe slightly less, right, when it was the hot subject, right, of course, they had some models, some ideas, what might happen inside of the capacitor. And some physical model, right? And of course, with time, people realized that that model didn't make any sense. So of course, the model was abandoned, forgotten, right? But I don't know, for whatever reasons, the term got stuck. And we still use that term, right, displacement current. Maybe it had a meaning for that particular model, but now it doesn't have any meaning. It's just a fancy name, right? So it sounds cool, right? Why not? Right? Cool names, very important, right? For example, a couple of years ago, I was reading something, right? And I saw the name, the Institute for the Works of Religion, I think. I think it's called like this, right? Could you guess? Can you guess what does this institution do? The Institute for the Works of Religion. I would never guess. So I Googled and I saw it's just basically Bank of Vatican, right? So cool names, but probably this is the coolest name I've ever seen, right? Right? I would never be able to guess the meaning, right? So the same here, displacement current sounds cool, right? Okay, so that's what this term. So he introduced this term, displacement current, and he decided to try it. So he added it to Ampere's law. So now Ampere's law will look at this, will have this form. will look like this. So integral of the closed loop b dot ds mu naught I enclosed plus id. So this I enclosed, it's actual current, and plus displacement current. We will look at this deeper. Before we go into this equation and see if it works, let me emphasize on one important part. We introduce displacement current this way. And look at this expression. On this side, on the left-hand side of the equation, we have I. This I, it's an actual current which charges this capacitor. Actual charges, which consist of drifting charges. All right, so that is the actual current charging that capacitor. And on the right-hand side, we have whatever this displacement current is. Right? Actual current, whatever this is. But numerically, they're equal. You see? If we have here 5 amps, exactly the same 5 amps will be there. So this displacement current all the time equals numerically to the actual current. But it doesn't mean that their natures are the same. What do I mean by that? For example, let's say we have an elephant with the mass of, 2,000 kilograms, 2 tons. And let's say we have a bunch of mice, the same 2,000 kilograms. So their masses are equal, but it doesn't mean that their natures are the same. This is an elephant, these are mice, right? Although their masses are the same. So the same here. These currents, actual current and this displacement current, numerically they're equal, but it doesn't mean that nature of this current is the motion of charges. No way. So right now we don't know the nature of this, but we will discuss that. But numerically they're equal. I'm just trying to emphasize on that. Numerically they're equal because it's a very important part. Right, okay, so after establishing that numerically actual current equals to the displacement current, okay, so now we can write down explicitly the right-hand side. So that's what Maxwell introduced, right? And it worked. We will see, right? So it worked. So he fixed, and it's now it's called Ampere-Maxwell's law. Since he fixed it, he found the problem, he fixed it, so his name was added to the name of this law. It's not uncommon when several names are used to name a certain law. Like when I was in the university in Ukraine, we had one of the professors, he was like a star in the solid-state physics, right? He used to teach us quantum theory of solid-state physics. And in the solid-state physics, there is a law, right, which consists of 4 names, and his name was the last one. So the first name, then hyphen, the second name, hyphen, the third name, hyphen, and then his last name, right? Okay, so if you manage to find any problem with this law, and if you manage to fix it, then of course your name will be added to the end of this line of names. Why not? And Ampere-Maxwell Jones law. Okay, so now let's look at properties of this displacement current, right? And then we will see if this law fixes our problem. This form of the law fixes the problem which we saw. So properties. Again, I copied and pasted the same picture from the previous slide and the definition of this displacement current expression. So first of all, what can you say about the value of this displacement current outside of the capacitor? For example, over here. We still don't know the nature of this current. So for example, over here, outside of the capacitor, what's the value of this displacement current? You should be able to realize, right? So inside of this, we have electric flux. Of course, electric flux is proportional to the value of the electric field. And you remember a couple of months ago when we introduced this capacitor, what's the value of the electric field outside of the capacitor? Parallel plate capacitor. 0, right? 0. So since electric field outside of the capacitor is 0, it means that the value of this displacement current outside of the capacitor is 0. And it means that this displacement current can exist only between these plates inside of the capacitor. right? Because that's where electric field is, right? Which most likely changes in time because we're charging a capacitor. So first, displacement current outside is 0. Then, second, and also, a direction of this displacement current, whatever nature is the same as the actual current, direction of the actual current charging the capacitor. Then, second, in the previous slide, I spent like several minutes emphasizing that numerically, this actual current equals to the value of the displacement current. If we have here 5 amps of current, exactly the same 5 amps of current, displacement current, 5 amps of a displacement current. So now actually we have a true conservation of current. You remember we introduced, if you don't have a junction point in a piece of a wire, part of the circuit, if you don't have a junction point, then current must be exactly the same. It doesn't matter where you look. But if you had a capacitor, right, back then what we had. So here we had some current between the plates of the capacitor. There was no current. But now, since we introduced this displacement current, so we have true conservation of current. Here 5 amps, here 5 amps of current, and there 5 amps of current. So we have now, even if you have a capacitor in your circuit, still exactly the same current will be throughout the whole wire where there are no any junction points, right? Okay, so now exactly the same current. And the last one. This displacement current has nothing to do with a flow of charges. The actual current, this I, it's a flow of charges. That current has nothing to do with the flow of charges. Because there are no charges between the plates flowing, right? So why do we call it current? Because it produces magnetic field, like actual current. So this actual current flows, right, charges flows, and as a result, it produces magnetic field around itself, right? And we can find direction of those magnetic field lines by outstretching our thumb in the direction of the current and curling our fingers, right? So this displacement current also produces magnetic field. And again, you can find direction of the magnetic field lines in the same way. You can now stretch your thumb in the direction of the displacement current, and your curled fingers are going to give you magnetic field lines. But the nature of the production, magnetic field production, is completely different. Here, charges flows, charges move, and we know they give us magnetic field. Here, changing in time magnetic flux. Changing in time magnetic flux, and of course in a special case, changing in time electric field. This electric field, changing in time electric field, produces this magnetic field. Right? So that's the nature. So we call it current, and of course it has units of current because it produces magnetic field like if it was a current. But of course the nature of that magnetic field production completely different. This actual current produces magnetic field because charges drift. This displacement current produces magnetic field, which forms circles, because electric field changes in time. Okay, so these are properties. And now let's see if this Ampere-Maxwell's law fixes our capacitor problem, or problem in the presence of the capacitor. Okay, so you remember that picture? I just copied and pasted a couple of slides ago. That's where we realized that there is an issue. And so now let's apply this law for the surface S1 and for the surface S2. Okay, so let's start with S1, which is the flat one. All right, so Ampere's loop, right? You see Amperian loop and the flat surface S1. Displacement current over there, right? So for the surface S1, again, this is integral over the closed loop, Amperian loop, and then we're not now I in, this I in, it's an actual current. This I in, it's a current which consists of this of a drift of charges. And the displacement current, yeah, this finicky term, additional term. Right. So now let's see. Surface S1, it's over here. So which current crosses this surface S1? Obviously, displacement current is only between the plates. So the displacement current cannot cross that surface S1. So only actual current I crosses surface. So in this case, I in is our actual current I, and the displacement current is not there. So it doesn't cross surface, it doesn't cross surface S1. Okay, so now as a result, this is 0, this is I, so we're going to get mu naught I. Okay, that's for surface S1. Now let's look at this surface S2, this baggy type, which goes through the gap between the plates of the capacitor. Right, exactly the same, but now surface S2. And now let's look at the values of I enclosed and I displacement. I in, again, this represents actual currents, And so this is our surface. Does any actual current crosses surface S2? No. Again, actual current, current which is created by the drift of charges. No. I in this case, is 0. What about displacement current, the second term? Yes, our displacement current, newly introduced current, of course, it's between the plates, and of course, it crosses surface S2. And we also, in the previous slide, you remember I emphasized, and also I wrote it here, right? Numerically, the displacement current numerically equals to the actual current, this actual current. Again, nature different, but numerically they're equal. So we can write in this case I displacement equals to I. And as a result, this is 0, this is I. We're getting exactly the same answer. So now we don't have any troubles. Right? So now left-hand side's the same, right-hand side's the same. So it doesn't matter which surface now you pick. In order to find the enclosed current, you will end up with the same answer. So that's how Maxwell fixed it. And again, you see, as I mentioned to you, it wasn't derivation, it was like a fudging, right? And he applied it for this particular system, for a capacitor. And then he generalized it. And now this equation is used to describe any phenomena where it's applicable, right? So he sort of fixed this law for this particular situation, and now, and then it was generalized, and then you can apply it again anywhere in space, at any moment of time, if it's applicable, right? So now this is fundamental law. Right? Before it wasn't fundamental. Now it's truly fundamental. Unless somebody finds another example where it fails to work, but so far no one could find any troubles with this. So now this is true law. Okay, so now I just wanted to create a separate slide. So Ampere-Maxwell's law, right? Again, integral of the closed loop, mu naught, the actual currents, drifts, which consist of drift where charges drift, and this displacement current, right? So again, you remember the structure of all these fundamental equations. On the right-hand side of the equation, we have sources, which produces field on the left-hand side of the equation. So in this case, magnetic field can be produced by actual currents, again, drift of charges. And this displacement current, which actually, what is that? Changing in time electric field. Changing in time electric field. So now, you remember when we introduced Faraday's law, we first kind of surprised that electric field was produced by changing in time magnetic field. So now we have fields can produce each other, and now we have a the opposite is correct. Now electric field changing in time electric field can produce magnetic field. So now we have a complete symmetry. Magnetic field can produce electric field can produce magnetic field. These two worlds, as I told you before, world of electricity and world of magnetism, they're just basically inseparable. They're so deeply overconnected that it's impossible to separate them. So that's why this course is usually called electromagnetism. Right? Okay, so now fields can produce each other, right? And that's why this guy is jumping. He did the same when we saw that magnetic field changing in time, magnetic field produces electric field, right? And now, yeah, it's basically they're inseparable, right? So it's eternal dance of the electric and magnetic field. Okay, I just thought it's worth of creating a separate slide to emphasize on that again. Okay, so Faraday's law described electric field production out of the magnetic field. Ampere-Maxwell's law described production of the magnetic field out of changing in time electric field. Okay, so now the last, before we go to the last equation, so now I just wanted to put together that Faraday's law and these results of Ampere-Maxwell's law. You remember, if you have, in the Faraday's law, if you had a solenoid, an inductor, right? If you change current in time, magnetic field inside changes in time. This magnetic field changes in time. As a result, it produces induced electric field. You see the circles, red circles. And now, using this Ampere-Maxwell's law, if you have a capacitor where there is an electric field, and let's assume that you are still charging this capacitor. So as a result, electric field changes in time, can be, for example, growing. Changing in time electric field produces magnetic field inside of the capacitor. And those magnetic field lines, again, form circles. Magnetic field lines are circles, right? Again, and directions of those magnetic field lines can be found by applying right-hand rule, because we know direction of this displacement current. Outstretch your thumb in the direction of the current, and the same right-hand rule number 2 can be used to find directions of these induced magnetic field lines. All right. Okay, so we're not going to solve problems about this. So I'm just lecturing about this so that when you go to a higher level classes, you would be familiar with this on a conceptual level. Okay, so the last equation, the last Maxwell's equations we have to introduce before we're almost at the top of the course. So the last equation, in order to introduce it, we're going to just use the symmetry. As you see, there are lots of symmetry between the electric world and the magnetic world, except for one point. We already mentioned that, and I'm going to remind you about that in a few minutes. So anyway, let's use the symmetry. You remember, we introduced at the very beginning of this course Gauss's law for the electricity, right? So integral over the closed surface, E dot dA, dA is the element of the surface, small patch, equals to Q enclosed, charge enclosed by your chosen Gaussian surface, divided by epsilon naught. And if we have this equation for the world of electricity, there must be a similar equation for the world of magnetism in order to have symmetry. Because now we have one law, integral law, over a closed loop in the world of electricity, right? And then we also have a similar law in the world of magnetism. But integrals over the surface we don't have in the world of magnetism. So let's introduce it. So we're supposed to have something like this. So instead of electric field, we will have magnetic field. Again, the same integral over a closed surface, but now instead of E dot dA, we have B dot dA. And can you guess? And I think you should be able to guess, right? So what will be on the right-hand side of the equation? On purpose, I'm not opening this up for now. What will be on the right-hand side of the equation? And that's where symmetry between the electric world and the magnetic world breaks. Look at the structure of this law. These are charges. And We can also use a very fancy name for charges in the world of electricity, in the world of electricity, right? So how else can we call them? Charges. Electric monopoles. Electric monopoles. For example, positive charge, it's a positive electric monopole. Negative charge, point charge, it's a negative electric monopole. Electric monopoles. Now, so basically, on the right-hand side of the equations, we have monopoles. In this case, of course, electric monopoles. So, as a result, what should we have here on the right-hand side? Do we have magnetic monopoles? No. So far, no one has ever seen any single magnetic monopole. You remember we discussed like a couple of weeks or 3 weeks ago, I don't remember exactly, that of course it's not physically impossible. No one has proved theoretically that magnetic monopoles are impossible. It's just no one has ever seen them. As a result, of course, all equations must be written using that fact that no one has seen them. So, because there are no magnetic monopoles, the right-hand side of the equation is, why it's not opening, 0. Once somebody finds magnetic monopoles, of course, this equation will be immediately rewritten, and magnetic monopoles will be introduced. But so far, since no one has found them, the right-hand side of the equation is 0. So that's the last Maxwell's equations. So now we're finally at the top of this course, at the peak, and now we can finally state all the equations, Maxwell's equations. So now it's a big moment. So, and again, I sort of comparing, reaching this point, it's like reaching the top of the mountain. And of course, since the most beautiful mountain in the world, at least considered, Ampere-Maxwell, so I took that photograph over there. Okay, so now let's state all these Maxwell's equations finally. So the first one, Gauss's law for the world of electricity, which we just refreshed, right? Integral over the closed surface, it's a surface integral, E dot dA equals Q enclosed over epsilon naught. And all these laws I already mentioned to you, I think a couple of classes. They have exactly the same structures. The right-hand side, we have sources on the right-hand side of all these equations. And on the left-hand side, we have fields which are produced by those sources on the right-hand side. So in this case, point charges produces this electric field. So sources, fields, produced by these sources. Right? So in this case, the meaning of this law, point charges produces electric field. And of course, we call this Coulomb electric field. Okay, so it's called Gauss's law, and the physical meaning, electric field is produced by charges. Right. Okay, now the second, which we just introduced like a few minutes ago, similar, Gauss's law for magnetism. That was Gauss's law for electricity, and now it's Gauss's law for magnetism. Since there are no magnetic monopoles, we have this form. And so physical meaning, there are no magnetic monopoles. Basically, that's the point where similarity is broken between the world of electricity and the world of magnetism. There are no magnetic monopoles, only dipoles, right? So every time we have south pole, north pole, south pole, north pole, of permanent magnet, of a magnet, right? Okay, two equations. And both of them surface integrals. Surface integration, surface integration. Now, the last two equations, integrations over a line. So first, Faraday's law. Now you see integral over a closed loop. It's a line integral. E dot ds equals negative rate of change of the magnetic flux. Physical meaning, again, here we have sources, and this is the field which is produced. So changing in time magnetic field, basically inside it's a magnetic field, right? Changing in time magnetic field produces electric field. Induced electric field. That was the Coulomb electric field. This is the induced electric field. So Faraday's law, the name, meaning changing in time electric field produces magnetic field. No, the opposite. Changing in time magnetic field produces the electric field. Right. So Faraday's law. And finally, which we spent like almost a class modifying Ampere-Maxwell's law. So again, integral over a closed loop, like the previous one here, closed integration over a line, integration over a line. Right? Mu naught times I, it's actual current, drift of charges. And this is mu naught times a displacement current. So again, right-hand side sources, left-hand side field. In this case, magnetic field can be produced or is produced by actual currents, which consist of charges drifting in a certain direction. And magnetic field can be also produced by changing in time electric field. Inside of this flux, there is an electric field. Electric field changes in time, magnetic field can be produced. Ampere-Maxwell's law, and the meaning that magnetic field can be produced by those two sources. So now that's what we call Maxwell's equations. You can open any book of electricity and magnetism and you can find these laws. Right? Of course, they can be also rewritten in a differential form. Right now, they are written in integral forms. You see, integrals, we have integrals everywhere. Two integrations over a surface and two equations with integrations over a line. Two equations for the electric field, this one, and two equations to find magnetic field, right? So these what we call Maxwell's equation. What is still missing? Because what we are presenting right now, it's the foundation of electromagnetism. Foundation, it means if you know that, you should be able to describe any phenomena in the universe. Of course, electromagnetic phenomena in the universe. And of course, in the classical world, quantum mechanical world, push it aside. It's a completely different world. So what else needs to be added in order to have a complete set of equations? All these equations allows us to find fields, electric field, magnetic field. Great. Once you know electric and magnetic field, what else do we need to introduce? How do those fields interact with material? Right now, that equation is not here. We just know how we can find fields. But of course, all those fields are going to interact, with the current, with wire, with the charge, with my clicker, right? How can we describe interactions of these fields with the world? We need to introduce an equation. And we already discussed that in the past. Of course, actually, we had two equations, electric force and magnetic force. But we can combine them and introduce them as one equation to the foundation. Here, QE, that's electric force. And then Q times V cross B, that's magnetic force. But we can combine them, factor out Q, and this equation is called the Lorentz force. The Lorentz force law. So now this equation describes how these fields, electric field, magnetic field, right, E, B, interacts. Force, it's a quantity which describes interactions, how do these fields interact with the world, with the material. So now this is a complete set. Any electromagnetic phenomena you can describe using these laws. Again, Maxwell's equations, these four equations, that's what we call Maxwell's equations. And then we attach this force, and now these four equations plus this equation number 5, they form the foundation. Okay, so now we can feel happy. So now we finally reach the top. But it doesn't mean that after this the life will be easier. It's like if you ever ran Boston Marathon, right? So when you reach the Heartbreak Hill, which is near Boston College, everyone will cheer, right, you up, and they will shout that, okay, now it's all downhill, now it's all will be easy. No. It's still ridiculously painful. There are still small hills, right, and you'll still feel like ready to die, right? So from this point, I can say, no, okay, guys, now it's all downhill, but it doesn't mean that it's going to be easy. So now it means that we're going to basically start looking at applications. But before we go over there, let me state all the whole set of fundamental equations in the classical physics, basically for physics 1, physics 2, and physics 3. Some of you already covered almost all of them, but let's state all those fundamental equations so that you will have a sort of better picture. It's kind of fun and important to have a better picture of the whole thing. Okay, so now let me state all the fundamental equations. Again, classical physics, quantum mechanical world. At some point you will learn about that. But for now, these equations, some of these equations are not applied there. All right, so let's start from physics 1, which is basically classical mechanics. So which fundamental equations we used over there? Almost everyone knows those. Newton's law number 1, Newton's first law, Newton's second law, Newton's third law, and then Newton's law of gravity. It's all about Newton. Newton, 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 Newton. Kind of boring, right? Right, he was boringly productive, right? So, four fundamental equations. So, everything in classical mechanics can be described using these laws. Of course, if you use Newtonian formalism. In the higher level classes of classical mechanics, you will learn about Lagrangian formalism, Hamiltonian formalism, but it's just different. So, for now, in Newtonian formalism, these are 4 laws. Then, physics 2, which we just discussed, 4 Maxwell's equations and Maxwell's equations and the Lorentz force. Overall, 5 additional equations. That's physics 2. And some of you already covered physics 3. Some of you will take that course probably next semester, maybe next year. So that course is less productive. Only 2 fundamental equations. After 5, 4, and 5, 2 sounds kind of not very productive. So, but also very important. First law of thermodynamics and second law of thermodynamics. So, overall, 11 equations. Again, that's for physics 1, that's for physics 2, and this is physics 3. Okay, physics 3. Okay, so now, finally, as I said, we've reached the top. And now, basically, we just need to apply these equations. Okay, these equations, right? These our fundamental equations for something. And now we're going to move into optics. Why? Because basically, light, as we will discuss probably next class, because we're running out of time. Light is an electromagnetic wave. It was a huge discovery. It was like a shocking discovery, right? And again, it was done by Maxwell. We will talk about that next class after Thanksgiving, right? And basically, it means what? It means that optics, if light is an electromagnetic wave, and of course, electromagnetic wave can be derived from these Maxwell's equations. It means that light is electromagnetic wave. It's just one of the problems which can be solved using Maxwell's equations. It's just one of the applications of these equations. It means what? It means that the whole optics is not an independent world. It's just a part of electromagnetism. So now it sounds like we're creating this gigantic empire. First, when we started this course at the very beginning, we thought that there is an independent world of electricity, an independent world of magnetism. Then closer to the end, we sort of realized that they're inseparable. So we combined them, created this empire, right? Electromagnetism. And now this, and also people first thought that optics is the independent world, its own world, right? And now this world empire of electromagnetism is going to annex the world of optics. So optics will be just a part of this gigantic empire of electromagnetism, right? And Maxwell is going to, not going to, of course, justify this annexation of optics, right? Okay, but of course we will talk about that next class, right? Okay, so now, guys, so from now we will talk about optics. First about wave optics, and maybe at the end we will have maybe one class about geometrical optics, right? And I will send you the link to a video about traveling waves. Oh, just a second, let me hold you for one extra minute, right? About traveling waves. I will ask you to watch that video as a preparation, right? About what traveling waves are, justification of the equation, right? So it's the first time we will see a function which depends on two variables and so on, right? So I will ask you to watch, and then on at the beginning of the next week in our recitation classes, we're going to practice that. So first you will sort of watch and to be familiar with those traveling wave equations. And then in our recitation classes, we're going to practice them, right? Because we just need to save a little bit of time so that we can cover a little bit more material. So now, maybe like last year, I think I started practicing that. I send that video, students will watch, and then we will practice that. But I don't practice that, that approach. I know it's called what? Flipping classroom, I think, or turning inside out, whatever the name, right? It's only, for now, it's only one class. I decided to do this way. Okay, so homework due Sunday, don't forget, right? And then I'll see you next week.